Hi, I'm Grace McLeod, a PhD candidate in the Hanson group at Florida State University, and today I'll be talking about our recent publication in ACS Applied Polymer Materials, entitled Enabling Lower Energy Light Harvesting in Photomechanical Polymers via Triplet Sensitization. Mechanoresponsive systems span the field of materials research, and they include piezoelectric ceramics, magnetostrictive compounds, and shape memory alloys. These can be used for applications as actuators and sensors in robotics and drug delivery. When we talk specifically about photoresponsive polymers, these typically use an azobenzene moiety and direct excitation to garner a trans-cis isomerization. However, this yields low efficiencies and relies on high-energy UV light. Utilizing the carbon analog of azobenzene, stilbene, shown here, offers us the opportunity for greater mechanical force, but it does require even higher energy light for direct excitation, as illustrated by the transient absorption spectrum, where the cis isomer peak at 250 nanometers grows in as the trans isomer peak at 300 nanometers diminishes over time with excitation of 254 nanometer light. However, by employing a triplet sensitization scheme, we're able to use lower energy excitation to isomerize. This gives us improved stability and improved depth of penetration. Shown here, we see our cis and trans stilbene moieties, which can be accessed by direct excitation of high energy light. However, by utilizing an iridium sensitizer, which I'll call FERPIC, shown at the right, we can excite that iridium molecule with a lower energy light, and then by intersystem crossing and triplet energy transfer, we're able to access the lower energy triplet states of our stilbene moieties, which can then undergo isomerization from either cis to trans or trans to cis. We make our materials using a stepped growth polymerization. First, we synthesized our stilbene monomer, and then using a dianhydride and doping in 10 mol% of the FERPIC molecule, we're able to get our polyamic acid solution. To finalize our film fabrication and polymerization, the stilbene polyamic acid is drop cast onto a clean glass slide. And then a thermal imidization process gives us a cured film, and IR absorbance spectra confirm that we have formed new imide bonds. The film can then be removed from the glass slide using hydrofluoric acid, giving us stilbene polyamide films. These films are then cut to uniform size with a 3 millimeter width and 20 millimeter length, and the width is ensured to be uniform across around 25 microns. And again, just to remind you, the stilbene moieties are highlighted in blue. That's our final polyamide film structure, along with the FERPIC molecule we're utilizing for our sensitized films. And ultimately, our film response can be summarized here, where the control film contains no FERPIC molecule. We're able to directly excite with 365 nanometer light and observe bending. There is a polarization dependence, whether that light is vertically or horizontally polarized. With our control film at 445 nanometer light, we did not observe bending. We know that we are not exciting the stilbene moieties directly. However, our sensitized film, which again contains 10 mol% of FERPIC, did demonstrate bending with the same polarization response and a similar degree of bending to our directly excited control film. And I mentioned there was a polarization dependence upon the bending of light. So whether the light is vertically or horizontally polarized, we see that the degree of bending does not change greatly based on the graph at the right. However, the direction does change. This can be explained by our proposed photoresponse mechanism, whereupon excitation directly with vertically polarized light, we get our cis-trans isomerization, followed by reorientation, which gives us a buildup of the trans-oriented normal to the vertically polarized light, and ultimately a strain gradient, where now our film is going to bend toward the light source. With horizontally polarized light, we again observe excitation of the Stilbene moiety, followed by a reorientation, which now gives us a relief gradient, and we observe bending away from the light source. The same direction dependence is observed for our sensitized FERPIC-containing films, where whether light is vertically or horizontally polarized, we still energy transfer and observe the same stress or relief gradient, giving us a bending again toward the light source with vertically polarized light and away from the light source with horizontally polarized light. Ultimately, the work can be summarized by the fact that we demonstrated the first use of Stilbene-Based Photopolymers, and we're able to successfully utilize a triplet sensitization mechanism for low-energy light harvesting in photomechanics. I'd like to acknowledge all of the co-authors on this paper, along with the Oates Group at FAMU FSU Engineering and the Kennemer Group at FSU Chemistry and Biochemistry, along with our funders, the Department of Defense, the National Science Foundation, and Florida State University. Please follow us both on this YouTube channel, give us a subscription, and at Hanson FSU on Twitter and Instagram for more photos of the beautiful work we do in the Hanson Group. Thank you so much. And please remember to read more in ACS Applied Polymer Materials.